Let's start back again on the cardiac muscle. Now, this is some of this is going to be reviewed because this is where I messed it up last time. I got it fixed, I think, this time, okay? So, cardiac muscle is only found in the heart. It's involuntary. It's cardiac muscle. It's not smooth muscle. It's cardiac muscle. It has its own blood supply. We watched the video the other day of the dissection, right? And we're talking about those coronary arteries. That's where it gets its blood supply, through the coronary artery system. Fortunately for you, I'm not going to make you memorize the coronary arteries. In anatomy and physiology too, you'll have to memorize the coronary arteries. So we won't do that. We'll look at a few of the big coronary arteries, but you won't have to remember their names. Because I don't remember their names either. I just know they're coronary arteries. In this you have coronary arteries and coronary veins. The heart also contracts on itself. Does anybody remember the 3 properties of the cardiac cell that we spoke of? You can look at your notes. Go ahead. The first one, you had the cell. Huh? Excitability. They give you a hint. Excitability. Contractility. Automaticity are the 3 properties of the cardiac cell. The cardiac cell, we will probably spend 3 class periods talking about the cell itself when we get into the physiology. Y'all understand physiology, right? I keep throwing that word out there. Anatomy is what? Pieces and parts. Physiology is the way that it works. So when I say physiology, I'm talking about the way that works. Something works. So the cardiac cell contracts on its own. It is so cool to watch. I'll find the YouTube video. They have all these cardiac cells out there, and they put a little epinephrine in there to get it to contract. And one cell starts to contract like this, and this cell is not contracting. That cell will move over. As soon as it touches this cell starts to contract. Then all of them start touching together and they start to contract. It's really cool to see. But not necessarily right now are you responsible for that 3 properties. I just want to bring that out that it is. This is the heart that we looked at already. We had the coronary arteries. We talked about the fatty stuff on there, right? So that's probably an abnormal amount of fat for this particular heart. That's why I don't know if that's why it ended up killing this person, but I do know on this side, we look at this graft here. They've had open heart surgery. You can see the stitches and then see the plaque that's built up inside the aorta. This big vessel right here. See all that plaque that's built up. One thing that plaque does is it decreases the elasticity of the artery. It doesn't allow the artery to expand and contract the way that it should. And it also increases the blood pressure. So the more plaque that you can keep out of your vessels, the better off that you will be. Learn that now. Don't learn that when you're my age, because you won't be able to function the way that you would want to if you wait that long. Did you have a question? No.
Is there a surgery for removing that plaque from the cell, or through the secondary?
They have some. They can go in there in some of the vessels and sort of scrape that plaque off. Yes, but it's not that safe. They start breaking that plaque off, it can easily travel in the bloodstream and become a clot. And we'll talk about that when we talk about heart attacks. Here's sort of a very simplistic picture of the heart. And when we look at this, it's good for you to start out with. And then this way you can sort of memorize the blood flow of the heart. Blood flow comes up through the inferior, which is towards the feet, right? And superior vena cava, which is towards the head. The vena cava is the main vein in the body. All right. So all the other veins will connect back into the vena cava somewhere. So you have blood flow coming up from the inferior and superior vena cava. What happens is the blood collects in the right atrium. The atrium are on the back side of the heart, sort of on top, and it collects there. Both atrium contract at the same time. The atrium contract in a downward motion. So when they contract, they push the blood down, both at the same time. The right and left atrium contract at the same time. So when the atrium contract, it pushes this blood through this first valve, the tricuspid valve, and you have the valves in that handout that I gave you, okay? But it pushes it through the tricuspid valve into the ventricle. Now the ventricles contract at the same time, and the ventricles contract in an upward motion, an upward squeezing motion. So if the heart's here, it squeezes the blood upward like this. It pushes it upward. This part of the heart, this area here, the pointed area, is called the apex. And it's because of the shape. This is the apex of the heart, and the top part of the heart is considered the base. So the blood is in the ventricles contract. When the right ventricle contracts, it pushes blood up through the pulmonary valve into the pulmonary artery. Remember, the artery carries blood away from the heart, so it does still fit the definition of an artery. From here, it takes it to the lungs, and it goes through the pulmonary system, the lungs, pulmonary, where it's reoxygenated. Once it's reoxygenated, it's transported back to the heart to be pumped out to the rest of the body. It's pumped back to the heart through the pulmonary veins, and it ends back up into the left ventricle. When the atrium contract on the left side, of course they contract together, but when the atrium contract, it pushes blood back down through the mitral valve or the bicuspid valve. Either one is fine. Mitral or bicuspid valve into the left ventricle. Then when the ventricles contract, it pushes blood through the aortic valve into the aorta, and the aorta is the main artery in the body, and then the blood flow, all the other arteries branch off the aorta. Then it goes through the cell, like we've seen here, and diffusion takes place in the cell the same way that it takes place in the pulmonary capillary. And oxygen is transported out, carbon dioxide is transported in through that process of diffusion. This whole process is called the Fick, F-I-C-K, Fick principle. I guess Fick invented it, or discovered it, right? I'm not sure of the name. That is the pathway of the heart. That's what you have to memorize. You have to get that in your head enough where you, when called on, you can stand up here and regurgitate that blood flow through the heart. So start studying on it now. And like I said, that handout that you give, that's a quiz. That's one of my common quizzes I give. So what will happen is I'll say, why don't you come up and give us blood flow through the heart? And let's just, you going, oh, I can't do that. You can't do it. And I said, well, why don't you come up and do it? So once you sort of start seeing that all that knowledge is going away a little bit for the majority, then that's where you get these quizzes that you've already had, even on the bones and all that. We want to keep that knowledge fresh. All right? So in that paper I gave you as well, the pathway of blood to the human body will help do that. These just tell you what I already told you. The right atrium receives blood flow from the vena cavas. The right ventricle pumps blood to the lungs. The right atrium receives blood from the lungs. and the left ventricle pumps it out to the body. I can guarantee you're going to see those again. You have to understand what each function of the atrium and ventricles are soon. And then the 4 valves. So when you look at the heart, you have a pump that has 4 chambers and 4 valves. You also look at a 2-sided pump that we'll get into probably in the next 8 weeks or so. You have a right-sided and left-side pump. So you have the heart is a 4-chamber, 4-valve, right-side pump, left-side pump. They operate together in sequence, and they're very good at that because the normal heart rate should be regular. You shouldn't have an irregular heartbeat. And it works in nice, good, it's all together. It syncs together. When it's not syncing together, it's outside of the word homeostasis. Remember we talked about that word? Balance. It's outside of balance. Something's wrong there. And a lot of times that's where you have to come in and fix something. Correct? All right, so we talked about the blood flow. Now, because the heart is an independent organ, it has its own conduction system or electrical system. Me picking up my stick relies on the brain. The brain has to tell the hand to go over there, we'll walk over there for one, and pick up the stick, right? And then once I pick up the stick, all these neurons are firing. The heart doesn't require that from the brain to fire, to depolarize. It has its own electrical system. So let's start up here at the top. This sinus atrial node that's in the right atrium, or the SA node, sinus atrial node. The sinus atrial node is the primary pacemaker of the heart. It sets the rhythm of the heart. Okay? The average the normal heart rate of an adult is 60 to 100 beats per minute. It's the normal heart rate of an adult. What happens in the SA node, since it's the primary pacemaker, it will build a charge and discharge. Build a charge and discharge. 60 to 100 times per minute. Now what you will hear, the terms you will hear with this, is it depolarizes, it fires, the SA node fires. When I say SA node fires, it really means the SA node depolarizes. But those terms are interchangeable. So what happens here in the SA node builds up a action potential, and it looks something like this, okay? Probably not that slow. And then it depolarizes. Nah, that's not a very good drawing. Disregard that. It builds up and it depolarizes. Builds up and depolarizes very fast because it's depolarizing at a rate of 60 to 100 times per minute. 60 times per minute, okay, is 1 per second, right? So it's doing this 1 time per second. The average heart rate for an adult is somewhere between 70 and 80. So it's doing it faster than every second. So the SA node will build a charge up and depolarize. Once it depolarizes, there's a line that's not on here. You can draw on yours if you wish. There's a fiber that comes across here called the internodal pathway. Inter means what? I-N-T-E-R. Have y'all got to the I's yet? Means between. So the internodal pathway, so there's a line here that shoots from the SA node to the left atrium. And when the left atrium depolarizes, it sends that impulse over to the left atrium, and both atriums contract. Everybody good? Once the atriums contract, once the SA node depolarizes, this signal comes down here to the septal wall where the AV node is. The AV node, atrial ventricular node, it's just there because of the location. Atrial ventricular means it's in between the atrium and the ventricles. You have this node sitting there, the AV node. The purpose of the AV node has only one purpose. It's to slow the impulse down. So the SA node builds the charge, it depolarizes, it goes over to the left atrium, it goes down this pathway to the AV node, and then that signal pauses just for a sec, not even a second, but a very, very short amount of time, and then it travels on. Because what happens is, what needs to happen is these atrium have contracted, right? They've pushed. Once the SA node fires, the atrium contracts, and it pushes blood through their valves, correct? The tricuspid valve and the mitral valve. So blood goes in the ventricles. What do the atrium need to do now? What do they need to do? They just pushed all that blood through to the ventricles. What do they need to do? You're right. They need to get more. They need to refill. So you have what's called refilling time. The atrium need to have a refilling time. If it wasn't for this AV node, the signal would go from the SA node all the way to the end here without any pause, and you would lose your refilling time. Your atrium wouldn't have time to refill. And then that, in theory, that SA node would depolarize again, and there wouldn't be anything there, right? Wouldn't be any refilling time. There'd be very little blood there. All right. That explains a lot of stuff, by the way. We'll talk about, like a rapid heart rate. Why someone gets dizzy when they have a very, very rapid heart rate, because they're decreasing their refilling time. Okay, so it pauses right here, and then it releases it. The AV node releases it. It bifurcates two paths, the left and right bundle, and it goes through these bundles here, bundle branches, and then it ends up at the terminal end at the Purkinje fibers. Check the spelling in there. Purkinj something, right? Purkinje fibers. When that signal reaches the Purkinje fibers, then the ventricles contract. And when the ventricles contract, they contract in an upward motion, forcing the blood out through the pulmonary valve and the aortic valve. Then what do they need to do? You're right, they need to refill. So you have a filling, unfilling, refilling, unfilling, get the blood out, put the blood back in. Constant sequence. Ba-boom, 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 right? That happens all the time. Automatically. Automaticity. Once it starts firing, it doesn't stop firing until something really bad happens. If the SA node stops firing, fortunately, we're not going to talk about it today, but fortunately the body always has a backup system. You'll learn about the first backup system when we learn about the Heimlich maneuver. When someone's choking and you do the Heimlich and it forces air that's left in the lungs to remove the object. That's one of the backup systems. Another backup system is the way that we breathe. We have two different sort of pathways that we breathe. Real bad chain smokers breathe on one, healthy people breathe on the other. So there's backup systems to keep this running. We won't talk about they're called intrinsic firing rates, or intrinsic inside. So the heart actually has 3 or 2 more intrinsic firing range to keep it pumping that we'll learn about later. But does everybody sort of see how that electrical pathway works? It's a matter of charging, discharging, electricity moving through the pathway. It stops at the AV node for a very, very brief time. Then it's released into the bundle branches to the Purkinje fibers. The energy is released into the ventricles. The ventricles contract and pushes the blood out. It's a pretty neat system, right? This here is just a representation. You see the lungs here and the heart. Different pieces and parts. We'll watch a video later where you've already watched the dissection one, but we got some videos that sort of give you a good idea of what your parts really look like inside. Alright? You need to know that. Let's look at something right quick that I want to show you about this electrical pattern before we stop. Everybody has seen one of these, correct? At least on television. That's a normal, well, besides my horrible drawing, that is a normal ECG complex. That's normal. When you see that, that would be somewhat normal. Okay? When we talk about medicine, and I teach you all this really cool stuff, you have to know what's normal and abnormal. Normal, abnormal. So when you look at it, you would say abnormal. Okay, I got what that looks like. Not normal. Normal. Abnormal. Normal. So when you look at things, that's in order to figure out what's wrong, you have to know what is normal and what is abnormal. If you don't know that, you can't figure it out, right? Nobody can. I can't. If I don't know the norms, I can't figure out if it's abnormal. I know our social norms. It is abnormal for someone to stand in public and urinate. That's abnormal. Correct? Because the norm is we go into the little bathroom and urinate in porcelain. In Morocco, that's not abnormal. You urinate in public. Men do anyway. Okay, so that's normal for them to do. So we have to know what's normal and abnormal all the time. This representation of this ECG complex is normal. When you have here, this first part is called the P wave. When you see that on an ECG, that P wave represents the depolarization of the SA node. Now, the ECG only measures electrical activity. Doesn't do anything mechanical. So we don't know if that heart contracted or not. Those atrium contracted because that's mechanical, correct? All we know electrically that the SA node depolarized because we had this P wave. We know that this is a P wave because it fits the definition of a P wave. Not that you need to know that right away, but the definition of the P wave is a P wave is upright, well-rounded, preceded by or followed by one and only one QRS complex. So I know that definition, so I know that that's a P wave because it's upright, well-rounded, and it's followed by this, which is the QRS complex. So it fits the definition. You fit the definition of a boy, correct? Correct? You fit the definition of a girl. Definitions in here are very important. If it doesn't fit the definition, then it's not that. All right? So we look at that. Now we go on, and we have the QRS complex like this. This is the QRS complex. The QRS complex represents ventricular depolarization. So when you see this on an ECG, you should be able to feel a heartbeat. You should be able to feel a pulse. So if you were to see that on an ECG and you were feeling a pulse, the normal would be that you see this complex and you feel the pulse, because that represents the ventricles have depolarized. And the norm for when the ventricles depolarize, they contract. All right? So if we were to break this down, QRS, they have to leave it simple, right? For us. So the Q wave is right there. The Q wave, by definition, is the first negative deflection off of this invisible line that runs through here, called the isoelectric line. Iso meaning neutral. So when you see that prefix iso, it means whatever that is, it's neutral. Isoelectric, it's a neutral line. It's not positive or negative. QR, the R wave, by definition, is the first positive deflection off the isoelectric line. So you have the Q wave, first negative deflection, R wave, first positive deflection. You only have one left, the S wave. What do you think the S wave is? Huh? Well, by definition, what is the S wave? It's easier than that. You're overthinking it. The second negative deflection. Okay, see what I mean? Easy. So the QRS, Q, first negative deflection, R wave, first positive deflection, S wave, second negative deflection. Then the last structure you see here, right here, is the T wave. What the T wave represents is ventricular repolarization. So that's when the ventricles are repolarizing. They're building up that next action potential to discharge. So you have charge, discharge, charge, discharge. This part right here, just in case you're getting some kind of ECG trivial pursuit over the weekend, this part here, in just a minute, this part here represents the AV node. Because when you come across here in time, okay, when you go left to right, this equals time. This up and down equals deflection, or millimeters. So time comes across here. This, it's called the PRI, but the PRI represents the pause at the AV node. Isn't that cool the way that works? You can tell a lot about the heart by knowing how to interpret that EKG. Tells you a lot of information about the heart. Questions?